Thank you for the opportunity to speak here, and thank you everyone for coming. So I'm going to present sequences of manifolds with lower bounds on their scalar curvature. A lot of what I'll be talking about today are conjectures that were devised during the IAS working group on scalar curvature and convergence in 2018. So I just thought I'd include some of the photos from the people who were there. Everything that I'm presenting here is presented in much more detail and many more conjectures than what I have time to talk about today in the chapter Conjectures on Convergence and Scalar Curvature, which will be in the new book Perspectives on Scalar Curvature, edited by Gromov and Lawson in World Scientific, that's appearing this year. The preprint for this chapter is on the archive. There are almost 150 citations in this chapter, so I apologize that I won't be able to mention everyone during this talk who has contributed to these problems and have done partial results in these directions. So I will just give a very brief survey. It's a short talk and give some basic ideas of what we were discussing and what we would hope to continue discussing during this not only scalar curvature seminar this spring. So just one new set of ideas to discuss here about convergence. All right, so suppose you have a sequence of three-dimensional Riemannian manifolds with scalar curvature greater than or equal to 0. And this, just for the sake of the talk, I'll just stick to non-negative scalar curvature to keep things simple. Suppose you have MJs converging to some M infinity in some weak sense, and the pictures could look something like this. Then what properties of non-negative scalar curvature persist on the limit space M infinity? What additional hypotheses might be added about MJ to provide stronger controls on the limit space, M infinity? What additional hypotheses might be added about MJ to guarantee there is a subsequence that converges, so a compactness theorem, for sequences of manifolds with scalar non-negative? And what notions of convergence might we consider? So I'm going to present some examples and conjectures and a few of the results, but there are many more results I just don't have time to discuss. But I'd like to try to get to the examples as the primary topic of today, in part because these can be drawn and it makes a nice set of pictures for everyone to keep in mind for the rest of the spring.
Christina, are you
Yes.
requiring M infinity to be a manifold or not necessary?
It might not be, right?
Okay.
Yeah. At the moment, this is very vague, right? Yeah. So if we, let's just talk about some constructions of three-dimensional Riemannian manifolds with scalar non-negative. So the scalar curvature could be, this is how it's defined on a Riemannian manifold, but of course we have already seen Misha already speak about the various notions of scalar curvature, and I just repeating this one here. This is not as useful a definition as others, but it is a true fact that scalar curvature at a point P in a Riemannian manifold is the limit as R goes to 0 of 6 times n plus 2 of the volume in Euclidean space of a ball of radius R minus the volume in the manifold we're talking about, divided by R squared volume of Euclidean space. So if you look at this definition, you can immediately see that a flat 3 torus whose small balls are Euclidean will have 0 in the numerator, so it has scalar equal to 0 everywhere. And the standard 3 sphere, you do a very straightforward, easy calculation, L'Hopital's rule, twice, and you get scalar is equal to 6 everywhere. Another example with 0 scalar curvature is this parabolic Riemannian Schwarzschild space. Now I mentioned parabolic to emphasize the point that this manifold is a parabola rotated around a sphere. So this is Riemannian Schwarzschild space. It's a warped product Riemannian manifold that has scalar curvature equal to 0, and it is the part of a Schwarzschild black hole. The fact that this is a parabola here is rather important because it becomes asymptotically flat in a very nice way that will allow us to use it to glue together some examples. For example, you could take a sphere, you could cut out a ball from the sphere. So this is a three-dimensional sphere. Cut out a ball, glue in this part of the Schwarzschild space over here, running from the red to the blue neck point. then glue a cylinder here, and then glue a cap. So the cylinder has positive scalar, the cap has positive scalar, the sphere here has positive scalar, and the Schwarzschild part has 0 scalar curvature. Run Ricci flow for an instant. This is only C0, this manifold. You line it up so that these are tangent to each other. And this will be a nice C0 Riemannian manifold. Run for 1 second Ricci flow, and it will be positive scalar everywhere and smooth. You can then glue many of these wells. So this is the standard gluing process to create wells. And you'll see that in order to do this, we have to consider smaller and smaller necks. But since this is a parabolic, this is a parabola here. If you rescale the Riemannian Schwarzschild space, you can get the neck arbitrarily tiny. And this red region can also be arbitrarily small, and this will be asymptotically flat. So it will glue to really small parts of a sphere. So a three-dimensional sphere with 3 wells attached. All right, if you make a sequence of manifolds, you can have the first one have 1 well, the second one has 2, the third one has 3, and go on forever, adding more and more wells that are narrower and narrower. The total volume of the wells could go to 0, and you will get what's called Ilmenen's example of a sequence of Riemannian manifolds, 3-dimensional Riemannian manifolds with non-negative scalar curvature that has no limit in the Gromov-Hausdorff or in the C0 sense. Okay, we can also construct M3 with scalar greater than 0 using tunnels. So you can glue the Schwarzschild and a cylinder between a pair of spheres to make the tunnels arbitrarily long and thin or arbitrarily small. So you have these, take the Schwarzschild here, so I drew it again. You can attach the 2 spheres, take a piece of the Schwarzschild up to the neck, attach a cylinder, but then open up again here and here. So now we attach it, run Ricci flow for a second, it will become smooth. You can make the neck arbitrarily small by rescaling this down. This will be attaching to the spheres here. So even though this is almost flat in this tiny spot, if you go far enough out with parabolic rescaling, it will fit. And then you'll have a nice C tangent. If you think of it externally, it will be tangent to the spheres, and then you will run Ricci flow for a second, it will become positive scalar. These have all been done earlier by Shane Yao and Gromov-Lawson, and they didn't write it as gluing Schwarzschild and running Ricci flow, but that's just the way I like to see it. It makes it easier for me to picture. So we can build MJ3 that have no CK or a Gromov-Hausdorff limit in this way. And here you'll see what I've done is the 1 well, 2 wells, 3 wells, and so on. And you can have these tunnels, and you can run the tunnel from a sphere to itself. So there's no reason that this is 2 different spheres. These could be, this red part and this red part could be 2 different balls in the same sphere. And you can make the tunnel thinner and thinner. The tunnel could become longer. This sequence has no CK or Gromov-Hausdorff limit. It does converge in the intrinsic flat sense, which I'll call Swift sense here, and in the volume preserving intrinsic flat sense. All right, so I will have to talk about these some more. But this is a notion of convergence that does work for these classic examples. It was designed to work for them. So which geometric properties of scalar non-negative persist on M infinity? Well, Bamler and Gromov proved that all properties on C0 limits, M infinity, that are smooth will persist. And the way they prove that is, I won't get into the detail, but they take a C0 limit, and Bamler uses Ricci flow and Gromov uses what's called Prism inequalities. And then they show M infinity has certain properties. And then since it was a smooth Riemannian manifold that they're assuming it's smooth, they can show it's a non-negative scalar. And then of course, all properties persist. But note that C0 convergence implies that the volumes, diameters, and distances converge. And so perhaps those are more important notions than to require C0 convergence completely. Maybe we should be able to get some results without assuming C0 convergence. Recall that our classic examples do not converge in the C0 sense. So if you have just a single well, there's no C0 limit, but you have what we call volume above, distance below convergence. So volume above, distance below convergence is a notion of convergence that says, let's assume the volumes converge. Let's assume the diameters are uniformly bounded above. And let's assume there's a C1 diffeomorphism, psi j from M infinity to MJ, such that the distances are bounded on one side. So it's called volume above, distance below, because the important point is that the distance is bounded below. So the distances on the sequence are bounded below by the distance on the limit. And the volumes on the sequence, well, they have to be above the volume of the limit, okay, because they're coming down to it. So they will converge down. The distances will be controlled from below. And if you have this notion of convergence, you can allow for wells. You can see that the psi j here is a radial map, and it will decrease distances, and the volumes of the sequence does converge. The diameters are uniformly bounded above. So this allows for one well, it allows for many wells, it allows for increasing sequences of wells. So you can ask which geometric properties persist on these VADB limits, volume above, distance below limits. And what about thin loops and changing topology? That won't be allowed. We can't have changing topology requiring that there's a diffeomorphism. So then you would need a more general notion of convergence. So that's when we come in with this notion of SWIFT, or volume preserving intrinsic flat convergence. Note that in joint work with Brian Allen and Raquel Perales, we proved that if you have this VADB convergence, then you will get the SWIFT, or volume preserving intrinsic flat convergence. So this implies this, and clearly C0 convergence implies the VADB convergence. So we have that this is an in-between notion that people can use to test ideas and see if we can get theorems like the one by Bandler and Gromov. If you assume M infinity is smooth and you have VADB convergence, do you get non-negative scalar? This is open. The same thing is open for SWIFT. But SWIFT convergence is a much more difficult notion, and so it's nice to have this in-between one. Note also that Allen and Perales have applied this notion of VADB convergence to solve some problems involving sequences of manifolds with non-negative scalar curvature, where there was no assumption of VADB convergence, but questions that arose from general relativity, they were able to show implied VADB convergence and then implied SWIFT. So it has already been applied in that sense. All right, but what is the SWIFT convergence? So this is a much more complicated notion. So let's just try to get through it. It's not too bad. It's a notion from geometric measure theory. So what we, Stefan Wenger and I defined this a number of years ago. And basically what we do is we take what we call the SWIFT distance, or intrinsic flat distance, between two oriented Riemannian manifolds of the same dimension. So we have the first one, M1, and the second one, M2. Here. And what we do is we take a distance preserving map phi1 and distance preserving map phi2 into a common metric space Z. Z is a complete metric space. And then we measure the distance between their images viewed as integral currents in the Federer-Fleming flat sense, which means you are filling in a volume between them, and you're measuring the infimum of all possible filling volumes plus filling of the boundaries. So when we take the subtraction, if you subtract these two, this is why there's an orientation. So you can think of Stokes' theorem. This is a subtraction of two Riemannian manifolds, images of Riemannian manifolds here. And we're asking that this image minus this image is the boundary of something one dimension higher, that's this yellow part, plus an extra piece of A, where because this boundary B might not be exactly M1 minus M2, boundary B might have some extra parts like this tall skin part or these little thin parts where the topology changes, or some wells. Those parts will be part of A. So as long as A plus the boundary of B is the subtraction, thinking in terms of Stokes' theorem as acting on differential forms, then this all can be tested. You take the area of A plus the volume of B, you take the infimum over all A's and B's, and that's the Federer-Fleming flat distance. This was used by Federer and Fleming to solve the plateau problem in Euclidean space. In order to make this rigorous, what I've just defined here, we need the notion of integral currents on metric spaces, because Z is a metric space, not a Euclidean space. So we use Ambrosio Kirchheim's integral currents on metric spaces, which is a beautiful paper. And instead of differential forms, they're tuples of Lipschitz functions that take their place. So this is quite a beautiful theory, Ambrosio Kirchheim's integral currents on metric spaces, and allows us to make this rigorous. Ultimately, we are not just taking a Federer-Fleming flat distance between the two Riemannian manifolds because they don't exist in the same place. We have to take distance-preserving maps into a common space C. This is imitating the Gromov-Hausdorff distance, which Gromov called the intrinsic Hausdorff distance, and this is why we call it the intrinsic flat distance. We take images under any possible distance-preserving map, and we're taking an infimum over all such images in all such possible complete spaces Z. And by doing that, we end up with a definition that's intrinsic. M1 and M2 do not lie in the same space. They're completely separate Riemannian manifolds, but we're now able to define a distance between them. This notion is very much like a kind of filling volume between them. It's a smallest possible way of filling it in. All right. When in this notion, we have then a class of limits.
It's not similar. Yeah. I think it's identical. What is the difference between these? If you forget about the boundaries, just minimal volume filling in. It's exactly the same definition. If you fill in,
only the boundary is different. Yes.
What your boundary? If you allow boundary, okay. And you don't need actually, in my view, mentioning actually this Ambrosio-Kirchen theory. You just say there are this
we do have to.
It will be definition can be done independently. When you prove theorems, when maybe you need it, but when you formulate it, you don't need it.
Oh, that's possible. The one thing I would like to emphasize that's a little bit different from filling Riemannian manifolds paper that you wrote is that the mass is here. We are, these are Ambrosio-Kirchheim's mass, which is a slightly different value than the weighted volumes used in that paper.
So it gives you actually different number. You say it's not the same
number. It
number.
gives a slightly different number. And the nice thing about the Ambrosio-Kirchheim mass is that it is semi-continuous.
Mm-hmm.
So when you have a sequence that converges in this sense, then the mass, the limit for the mass of the sequence will end up bigger or equal to the mass of the limit. So that's a very nice property of their mass.
And which kind of limits you may?
Yeah, exactly. Okay. And also under Swift convergence, the same thing will happen. Our limit spaces are what we call M-rectifiable integral current spaces. So the class of limit spaces is basically defined also using their theory.
Okay. Thank you.
Yeah, so thank you. The M1 and M2 then in general, I wrote the description of the definition here for oriented Riemannian manifolds with boundary. The general class of spaces that we can define this for are what we call M-rectifiable integral current spaces. So these are rectifiable spaces. That means that locally they have charts that are by Lipschitz equivalent to Rm, Borel sets in Rm. And the charts cover almost the whole space and they are weighted and they're oriented charts. And then there's a notion of boundary that's defined and the boundary is M-1 rectifiable and has finite mass as well. So the class of limit spaces is very much related to Ambrosio-Kirchheim's notion of integral currents. And then we have this nice mass properties. All right, so this is, so we very strongly use Ambrosio-Kirchheim both for the precise definition and for the limit space definition. All right, so then we continue here. And there's this possibility when we talk about, yeah, thank you. So there's Wencker's compactness theorem. This is in another paper. He assumes that if you have a sequence of Riemannian manifolds of the same dimension, and if you assume the volume of the manifolds and the volumes of the boundaries are uniformly bounded above, and the diameter is uniformly bounded above, then a subsequence Swift converges to a limit space, which is M-rectifiable. It's one of those currents, integral current spaces we defined. Or it could be the zero integral current space. So I just want to emphasize, what does it mean to say that the limit space is the zero space? It means wherever you have this red M2s, we replace it with zero. So it's sort of saying that M1 fills itself in. So this, for example, will converge to the zero space if the volumes of these guys converge to zero, because then it fills itself in with A and B could be nothing. Or if the filling volumes of these guys converge to zero. And that could be the same filling volumes as in Gromov's filling Riemannian manifolds paper. Those filling volumes converting to zero will imply the other ones converge to zero as well. It's just off by a constant. Off by a pair, a bounded pair of constants. Okay, so there is a possibility of things converging to zero. One should picture things like a tori that become thin will converge to zero space in the intrinsic flat sense. In the Gromov-Hausdorff sense, they converge to a circle. But the intrinsic flat convergence does not allow you to drop in a dimension. It will just go to zero space. So this is a notion for studying sequences that don't collapse. The possibility of collapsing to zero is a concern whenever you're studying a sequence. But it's really nice that there is at least this compactness theorem that says that if it's not the zero space already, it's nice and M-rectifiable space. And notice this compactness theorem has no curvature requirements. So we can use it to study sequences of manifolds with scalar curvature bounded below, okay? So we have some nice properties. The properties of the intrinsic flat convergence are if MJ converges to M infinity, then we get that in our paper, it's M rectifiable. It has a boundary that's M minus 1 rectifiable. The boundaries also converge, so the boundaries are limits. The lim inf of the volumes is bigger or equal to this mass of the limit space, which I'm just calling volume to be simple here. And in a joint paper with Jim Portuguese called Properties, and in a paper I wrote, Arzellis-Coley theorems, there are various theorems about points in the sequence converging to possibly, sometimes they disappear, sometimes they don't disappear. Like points at the tips of wells are considered to disappear. Points that are in regions with some sort of filling volume lower bound on the balls don't disappear, have subsequences that converge, and we also get that the balls about those sequences converge, but we have to do these almost everywhere things that are so common in geometric measure theory. And we have limits, so the volumes of the ball of the subsequences of balls converge are bigger or equal to the volume of the limit ball. And for scalar gradient equal to zero, we would really like volumes to converge. It seems that that's a very useful property to have. And we see here that we only have semi-continuity of volume. And that's why we've introduced the volume-preserving intrinsic flat convergence. So we say it converges in the volume-preserving intrinsic flat sense if it converges in the intrinsic flat sense and the total volume converges to the total volume of the limit or the total mass of the limit. Now, once you make that assumption, there's a lot of nice properties that follow. So Portuguese has another paper. In his paper, he shows that the spectrum of the Laplace-Beltrami operator has this nice property. The lim sups of each eigenvalue is less than or equal to the eigenvalue of the limit space. And Jorogui and Lee have proven that volumes of nice regions converge, including balls. So just assuming that the global volume is converging is enough to get volumes of a lot of regions to converge of various smaller regions. So that's a very useful property. And they apply this for studying spaces with scalar curvature bounds and positive mass theorem questions.
So I mean, there is no collapse, no collapse at all. That's the meaning of this condition. Right?
If you assume the volumes converge to the volume of the limit space, we're assuming there's no collapse, yes.
Yeah. No, but this implies there is no cancellation. This is the meaning of this, right?
Yes, essentially, yes.
Yeah. But the limit objects still don't have to be a manifold, maybe quite singular.
It can be quite singular. There are many examples that are very singular, and the limit space could be weighted.
But when you speak about Laplace operator, what do you mean when it's singular?
Portuguese has a definition that's a sort of min-max Raleigh quotient style definition, and it agrees with the eigenvalues on Riemannian manifolds.
Okay.
All right, so then we had a compactness conjecture that we devised while we were at IAS. So let me just bring it up piece by piece. So first we assume the volume's bounded, let's just have no boundary, okay? So suppose MJ3s have no boundary, the volume's bounded above and the diameter's bounded above, then already by Wenger's compactness theorem, a subsequence converges in the Swift sense to some M infinity that's possibly zero. And in the conjecture, we say, okay, assume also scalar gradient equal to zero and some other condition that will prevent collapsing. And one of those possible other conditions is min A is uniformly bounded below by a positive A, which means the minimum area of a closed minimal surface has to be bounded below by a positive number. And the conjecture is that we won't just have Swift convergence. If we add both of these properties, scalar and this one, then we should get volume preserving intrinsic flat convergence, and the limit space is not zero, and the limit space has generalized scalar gradient equal to zero. Now we can talk about other possible min-A's during the discussion later, but what I'm going to talk about today during this colloquium is the min-A condition in particular, and why that's one of the conditions we've decided to look at. And the chapter, yeah.
Since your conjecture, I don't think I contributed to that. You refer to myself, I don't think, if I wrote somewhere, I borrowed from you, no?
I will say I've adapted it. The min-A part, you could say I have. I would say that you have this conjecture even before IAS without the min-A.
Okay.
Yeah. There's a chat. Oh, yes. Thank you. That's the link for Portuguese paper. Portuguese paper is, of course, also cited in the chapter that I mentioned. Now this chat is sitting in front of my screen and I can't get it off. Okay, good. All right, so can we prove a subsequence of volume preserving intrinsic flat converges in special cases? So actually this has been proven by Park, Tian, and Wang. They proved the subsequence BF converges to if for warp product MJ diffeomorphic to S3. So this is a very simple case where you just have a single warping function, Fj squared R G naught is a metric tensor on a standard sphere with two closing on the either end. And they get generalized scalar curvature in limit space in the sense of H1 loc bounds on the limit F infinity. This kind of warp product can have one well, two wells, or no well, but it can't have increasingly many wells with this condition, but they are able to handle both kinds of wells. Other warp products are being studied by another team, including warp products that have functions of two different variables here. The graph and conformal cases are completely open and have not been studied yet. And now I wanted to talk a little bit more about why this min-A condition is needed to be added to this conjecture. The original conjecture did not have a min-A on it. And this is examples that I constructed jointly with Jorge Basilio and Joseph Dodzik. So remember, I had this thing about how we can have tunnels that are very, very small or very long and thin. And what we did was we just defined a notion called sewing tunnels along a curve. So if you have a sphere here and we have a curve, say along the equator here, this is a three-dimensional sphere. What we can do is we can cut out balls. So in our first Riemannian manifold in the sequence, we cut out two balls from a sphere and we glue in one nice fat tunnel. In the second one, we cut out pairs of balls in a pattern in which they're far, short, far, just like sewing. And we connect a tunnel for the ones that are far, and then you have to step into the world and then connect a tunnel for the ones that are far. And we do this. The next one will have 6 tunnels, the next one will have 8 tunnels, and so on. And we prove that this sequence Gromov-Hausdorff and intrinsic flat and volume preserving intrinsic flat converges to a three-dimensional sphere in which the path along which the sewing happened is collapsed to a single point. So this entire red line is a single point in the limit space. So what we mean here is if this point here, where the thumb is, okay, there's a point here and there's a point here. The distance from this point to this point is to run over to the red, instantly over here, and then this piece of distance here. And the reason is, if you look at the sequence, you start at this point there, you run into the tunnel, you instantly jump to the other side of the tunnel, and you come out. Or in the next one, you run into a tunnel, instantly jump here, run out and in, instantly jump there and out. And you can take a careful estimate on how the distances converge in the long run. And it's as if this entire curve became a single point. So we call this curve eta, and we say it's pulled to a single point. That's a notion from metric geometry, saying that it's identified to a single point. And notice that the volume of the ball about that point, that red point of radius r inside this limit space, is equal to the volume of tubular neighborhood of radius r of eta in a standard S3. And because of that, the scalar curvature at P is equal to negative infinity if you calculate it using that limit process. So these are increasingly tiny minimal surfaces in the sequence, because in the center of every one of these tunnels, this is what the tunnel looks like. And in the center of every tunnel is this neck point, and that's a sphere, that's an S2, and that's a minimal sphere. So we've got increasingly tiny minimal surfaces in the sequence. So we could prevent a bad sequence like this if we say that there's a uniform lower bound on the the area of a minimal surface. All right, another reason to have areas of minimal surfaces as a fundamental part of a conjecture about scalar curvature is because of these properties proven by Shane and Yao. So if you have a surface sigma 2, it's a stable closed minimal surface. It minimizes area of any continuous deformations. So you can talk about these guys even in less smooth spaces. You can talk about a minimal surface. Here's a picture of one where this is an S3 and there's an S2 that's a minimal surface. Here is a flat torus, a flat 3 torus, and this is a flat torus shaped minimal surface here. And Shane and Yao proved that if G is a C2 Riemannian manifold, then by taking the second variation of area and applying the Gauss-Bonnet theorem, the only stable closed minimal surfaces in M3 with scalar non-negative are tori and spheres, looking like these two pictures. And they have the torus rigidity theorem that says M3 with scalar gradient to 0 homeomorphic to a torus, then M3 is isometric to a flat 3 torus. Okay, so we have this as soon as this minimal surface is a torus, it starts becoming flat, and they get the whole torus rigidity from there. All right. So does torus rigidity hold on M infinity if you assume that the scale of the MJs is greater or equal to -1/j? So we would call that stability of the torus rigidity theorem, or we could call it almost rigidity. Okay, so you consider that's a property of non-negative scalar curvature that we would like to see holding on limit spaces. So that has actually been solved by some people, and I give the references under certain additional hypotheses on the sequence. So those references are in the chapter. So we have Kazar and his collaborators. We have Cabrera, Pacheco, Perales, Ketterer, Allen. There's many results on this torus almost rigidity. Each one, they assume some extra hypothesis on this manifold so that they're able to control things better. So there's quite a bit of results in this area. All right, so let's go back to this one, which is Gromov's conjecture with the min-A condition added to it. And now we know why I'm suggesting the min-A condition. And if you wish to suggest a different condition that would still give global volume preserving intrinsic flat as a conclusion, you do want to avoid these thin wells, the sewing properties. So you can try to avoid it in a different way. But I was very vague here about what generalized scalar non-negative is. And so I have to describe that a little bit more. So let's look again at the work of Gromov and Bamlow. They showed all properties of scalar non-negative persist under C0 convergence to a smooth limit. So what about the scalar non-negative on the VF and the Swift limits? This is very open. There are many results assuming additional hypotheses that are reviewed in the survey chapter. Most of these results are the global kind of results, things about positive mass theorem and things about torus rigidity. There's no local results yet that hold in general. So it's always results along the lines of assume it's a graph manifold, assume it's a warp product manifold, and then show that positive mass theorem holds on the limit space, or show that the torus rigidity theorem is stable, the positive mass theorem is stable or almost rigid. So these are the kinds of results that exist. There's many of them and they're surveyed there. If we wanted to define a generalized scalar non-negative, certainly this definition is definable on a space that is not smooth. And under volume preserving intrinsic flat, we do have volumes of balls converge, but this is very misleading. This limit is really a second derivative of volumes because of the L'Hopital's rule coming into play when you take the limit. So this volume limit is not directly preserved as MJ volume preserving intrinsic flat converges to M infinity. Nor does this property imply any global consequences on M infinity anyway. So this is generally a useless property of scalar, although I would like to see it to hold on the limit spaces after the fact. Theorems that do involve volume preserving intrinsic flat convergence show hypotheses on MJ related to torus rigidity and rigidity of the positive mass theorem imply global rigidity properties. Okay, so they strongly use the extra hypotheses and they directly estimate the Swift distance to a specific flat limit space. So the ones that have been proven so far are not general like compactness type theorems, except for that one that I presented already for the warp products. They are I know I want to show that the limit space is a flat torus. So now let me exactly estimate the Swift distance to a flat torus by putting them into a common metric space and taking a very precise estimate. So that's the way things have been done so far. We would like a quasi-local property that implies all these global properties. So instead of just proving something global, we would like to prove a quasi-local property. That would be a not infinitesimal. This is what I would call an infinitesimal property, and not global like these ones, but something quasi-local that says balls of a certain size or something of all scales has a property. So the Prism inequality is one of the best candidates for this. And it is the one that was used for the C0 convergence by Gromov. So let's just talk a little bit prisms and dihedral angles. If M3 has scalar non-negative, then any cube P3 in M3 satisfies prism rigidity. That is, if each face is mean convex, so here I have a mean convex faces. At any P lying on the edge, the dihedral angle here is greater than or equal to pi over 2, then P is isometric to a rectangular prism in Euclidean space. So you can't have this kind of bowing out that I've drawn here with scalar non-negative inside. It just instantly becomes absolutely flat. So here's a reminder what mean convex means. It means local outward deformations have areas that are increasing. So that's a notion that can be defined with very low regularity. The dihedral angle at P between two faces at P, well, that's a notion that kind of needs angles. And so that would kind of require a little more.
Wait, one remark. Just when you prove something, it's no good to have external deformation. You need to prove existence of contracting internal deformations. You see, for example, to have maximum principle or whatever, you need that. And if metric is not smooth enough, it's not the same. Having enlarging external deformation and existence intrinsically smoothing, decreasing area deformation, it's not the same. For metric already, we see one smooth only. Definitely not true for continuous metrics. So be very, very careful what you mean curvature. It becomes ambiguous, yeah. For external deformation, I would never claim this as a definition, yeah. You see?
I see what you're saying. Yes, yes.
Because first, to start with, there is no kind of external. No,
well, it's sitting inside an M3, but I see if you're saying C0 metric, that's not going to work.
They're not the same. They're not the same. For non-smooth spaces, even for Riemannian, but definitely not for continuous. I'm not remember for C1. Yeah.
Okay. And the dihedral angles, you would like a notion of angle?
Angles, okay. Angles defined, yeah, is rather robust.
Yes. So I'm going to talk a little bit more about angles in a minute. All right, and if M3 is smooth, then prism rigidity for all cubes implies scalar non-negative everywhere. And even without smoothness, prism rigidity for all cubes implies global consequences like torus rigidity. So this is the kind of property where I'm saying the quasi-local property that implies the global properties we would like, that implies scalar non-negative. That's a natural definition then for what we mean by generalized non-negative scalar curvature. So this is one reason why I put your name on the conjecture, because this was your suggestion, Misha, right? Yep. All right, so if MJ have scalar MJ greater than or equal to 0, does M infinity have prism rigidity? So does prism rigidity hold on volume preserving intrinsic flat limits? So I'm just going to give an example here that isn't in any paper, but I just wanted to draw it up here. So suppose you're gluing together cap spheres. So we have a sequence of N1, N2, they're cap spheres. There's C0 converting to a pair of flat disks joined along S2 boundary. Okay, so this is a double disk. So you have C0 convergence of N1, N2 to a double disk. And then that's a volume preserving intrinsic flat. And now I'm going to construct MJs out of this sequence, because I'm going to take a sequence of these A to 1, A to 2, A to infinity. These are curves. I'm going to sew tunnels along these curves. So the first one will only have one tunnel. The second will have 2 tunnels. The next one will have 3 tunnels and more tunnels. And we'll see that we get volume preserving intrinsic flat convergence of these MJs, which will have non-negative scalar, to an M infinity, which is a double disk, but has a line segment pulled to a point. And so that N infinity, that M infinity that we get, which is this double disk with the with a line segment pulled to a point fails prism rigidity because it has a flat region with a curve A identified to a point. The flat region satisfies all the conditions of the prism inequality, except that there's this, it's not actually isometric to a flat prism in Euclidean space at the end. All right, this is not a terrible example. It's another one of these examples caused by the sewing, right? So the sewing is a technique that involves lots of smaller and smaller tunnels. So we just want to prevent sewing in order to allow prism rigidity to hopefully still occur. So again, the sewing involves many, many tiny tunnels. And that's another reason why I like to add min A greater than A greater than 0 as a hypothesis. Okay, so if we add that hypothesis, we won't have this non-examples. So does prism rigidity hold on limit spaces if we assume the volume preserving intrinsic flat convergence and we also assume the min A's bigger than 0? So that's a new open question. If yes, then this is the perfect notion for generalized scalar for the conjecture stated with min A. So now I'm going to write the conjecture one more time now. We're going to write that precisely the notion of generalized scalar is that prism rigidity should hold. All right, now to make sense of prism rigidity, so all the top is the same as before with the min A I put in, but other people can suggest others. To make sense of prism rigidity on M infinity, we have to, I'm going to make a few conjectures about what M infinity should be like, because so far the volume preserving intrinsic flat limit is rather, it's rectifiable, but it's not even necessarily connected. So I'm going to conjecture also that the limit space is connected with geodesics between points and that it has Euclidean tangent cones almost everywhere so that we can define angles. So we can add these to the conjecture as various properties we would like to see on the M infinity space. All right. All volume preserving intrinsic flat limits are rectifiable. So they have the bi-Lipschitz charts and they have tangent cones almost everywhere, but the tangent cones might be norm spaces. And if they're norm spaces, then we won't have a definition of angle unless it's a Euclidean norm. Okay, so that's why I was conjecturing that the limit space would actually be Euclidean. So we'll see. And they don't necessarily have geodesics in general. And sometimes they would be 0 spaces, like when it collapses or the filling volume converges to 0. So we have to avoid all of those possibilities. This talk is almost done. I'm just going to draw 2 more sets of examples. So the examples that exist, if we have scalar gradient equal to J, I can make examples that contradict all of these, but they all have the tunnels and the min A goes to 0. So let's just draw these examples. There's one set of examples with Basile and Sormani and, Basile and I. We take an increasingly dense collection of balls in S3 and we connect them by tunnels. Now, these tunnels will be short and tiny tunnels. I know they look long here, but they're short and tiny tunnels. And notice this pattern where we take between every ball, we have tunnels running to every other ball. So this is a very nice transit system where you can run from without changing trains anywhere, okay? Ensure the total volume of the tunnels goes to 0 and your limit space is a single point and the Swift limit, the GH limit is a single point, the Swift limit is the 0 space. We could even restrict our tunnels to a domain U and not have them becoming increasingly dense, just increasingly dense inside U. And that would make that the GH limit and the Swift limit would be S3, where we identify U to a point. So we can get all sorts of bad examples using this process. Okay, so this is a process not sewing along a curve, but sort of sewing everything to everything else and just pulling it tight. All right, so then there's another kind of neat example, which is done with Basilio and Cazares. Again, it's the same picture, but now the tunnels are going to have a different length. So instead of making the tunnel short, we're going to say the distance between these 2 balls, the length of this tunnel will be set to the Euclidean 4-dimensional distance between these balls. So these tunnels are actually as long as they are in this picture. And when you do this, and you ensure the total volume of the tunnels goes to 0, you get volume preserving intrinsic flat convergence to S3 with the Euclidean metric. So it's a 3-dimensional integral current space, it's rectifiable, and it has no geodesics at all between any points. because it is not an inner metric space. It's the distance between points is the Euclidean four-dimensional distance. So that's a possibility that could happen if we're allowing tunnels of arbitrarily small size. This guy actually has Euclidean tangent spaces, so that's kind of nice. And to appear in the future will be examples where we can construct sequences with normed limit spaces that have scalar curvature greater than or equal to 0, constructed with lots of tunnels. So far, the examples with norm limit spaces that Stefan Wenger and I constructed do not have non-negative scalar. So what's to appear is three-dimensional manifolds with non-negative scalar curvature, converging to norm limit spaces. I don't want to describe that construction yet because it's not published, so we'll save that one. So now we've got this. We see that if you want to change, this is the hypothesis. This is just the conjecture again, exactly as I wrote it on the last slide. I just want to refer to it again. I know that there's some debate on whether we want to put the min AJ, and I do admit it here. See, I admit it, Misha. Okay, if anyone wishes to replace the min A MJ condition, this hypothesis, we now see the various examples of what we have to try to force not to exist, okay? So another condition would have to get rid of those examples. And we also would like to choose a hypothesis that isn't too strong because I'd like wells to still exist. So this min A hypothesis allows the existence of wells. It doesn't say that wells can't exist because they don't cause a minimal surface as long as they're decreasing as you go outward. And remember, we already have the Swift convergence. So the main thing, the first step towards proving this conjecture would be to try to show volumes converge. So it'd be really nice to know these four conditions, do they imply the volumes converge to the limit that you get under Wenger's compactness? That's the first Ah.
Right?
Yeah. So in the spirit of Penrose inequality, when we're doing I didn't talk in detail about the almost rigidity for the positive mass, we always delete the other side of the black hole.
Yeah, but here we see it's unclear who is a black hole, of course.
Yeah.
But again, when you have this limits, kind of, you can imagine that you sit at some point of your universe and many things happen and some huge pieces will slide away, but you only care for the piece which is around you. And the question is how to formalize it. So it's limit depends on the observer. Different observers will see different object in the limit.
Yeah, yeah.
So this is another point. Yeah.
That's another point, definitely. So all the other properties listed here about geodesics and these kinds of questions, all of them are open except for special cases of positive mass theorem and torus rigidity. There is also some Penrose stability type theorems as well. And you have to look at the chapter. And so I just ask everyone that if you're interested in the partial results to please look at this chapter. There are almost 150 citations, different papers that have partial results with different hypotheses. Lots of work has been done in the past few years. So I tried to include them. Anyone who's interested in papers about Swift convergence, I update this website all the time. This one has been sent to proof, so this one's not going to be updated. This will be continued to be updated. Anything that's related to intrinsic flat convergence will always be added to this webpage. If you want to learn more about intrinsic flat convergence, the rigorous definition, the details of various theorems and proofs, I have a lecture series at Fourier Institute, one at Fields Institute, and I had the original address about intrinsic flat at the Geometry Festival in 2009. So feel free to email me with any questions, and thank you very much.